At the end of our last video, we were discussing very briefly how to draw dot structures for molecules. We talked about how to figure out what the central atom was. It's usually the one you have the least amount of, as well as the one that is the least electronegative. And we also discussed the number of single dots on a central atom, as well as any other atom can tell you the number of bonds that it can form. Another way to draw out those dot structures, which is probably the better way, is to count the total number of valence electrons. And that's really helpful and important to do. You want to make sure that you have the same number of valence electrons in your diagram that you do when you initially counted how many you should have to begin with. Lines can also be used to represent bonds. One line is going to equal 2 dots. We're going to do a couple of examples on the next slide, and then you'll have a chance to try some later on as well. Our first example is Cl2. When you look at your periodic table, you should see that each Cl is 7 valence electrons. There are 2 of them, so 7 times 2 equals 14. One of the best ways to try to draw these, especially if you've never done them before, is to first draw what you have and add a full octet or 8 dots. Here we go. So Cl is connected to another Cl, and then I'm going to fill in all my dots. At this point, what I want to do is I want to count my number of dots to see if it matches the valence electrons that I would like. I have 2, 4, 6, 8, 10, 12, 14. So I end up with 14, which means this structure is correct. The other way you could have drawn this structure is like this, where you have a line that represents that bond. Either structure is perfectly fine. In our next example, water, we're first going to figure out the total number of valence electrons. There are going to be 2 H's, and they each have 1 valence electron for a total of 2. There is 1 oxygen, and it has 6 valence electrons. So when I add these together, I get 8. I have to then determine what element goes in the middle. I have 1 oxygen, so it's going to go in the middle. I'm going to, again, complete my octets. And I'm going to draw in my H's. At this time, it really doesn't matter where you put the H's. H does not want a full octet. It only wants to be in contact with 2 dots. As you can see in this model, it is. And then if I count up the total dots, I see that there are 8, which is exactly how many I want. So the structure is correct. Next example, PBr3. P has a total of 5 valence electrons because it's in group 5. And Br has 7 because it's in group 7a, and there are 3 of them. So 5 plus 7 times 3 gives you 26. Once again, we're going to figure out what goes in the middle. P is going to go in the middle, and then I'm going to add in everything else. Connect to Br, connect to Br, connect to Br, and then I fill in my octets. Once again, once everybody is happy, has a full octet, I count my dots. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we have the correct amount that we'd like. So our structure is correct and complete. Once again, please feel free to use lines when connecting elements. Just make sure that you count those as 2 dots when you're double checking. Next example is CO2. Carbon has 4 valence electrons. Each oxygen has 6 times 2 because there are 2 of them for a total of 16. Carbon's going to go into the middle. Again, we're going to fill in our octets. And we're going to count up our dots. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have a problem. At this time, I have 20. I don't want 20. So what I can do at this point is I can start to form some double bonds. I'm going to remove 2 electrons from here and 2 electrons from here. I'm going to instead make that a double bond. Now going to recount my dots. 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm at 18, so I'm still too high. I'm going to now move more dots to the middle. So these are going to go away. Those are going to go away. I'm going to put the dots in here. And when I recount, I am now at the correct amount, which is 16. So my correct structure for carbon dioxide should look something like this. Okay. Another way that you can draw these, if you prefer, which can be helpful, is to go right ahead and kind of just connect single dots. For example, if I redo carbon dioxide, carbon has 4 dots. Each oxygen has 6, so 1 comes in here. 1, 2, 3, 4, 5, 6. Same thing on the other side. 2, 3, 4, 5, and 6. And what I can actually do is I can move these single dots to the middle. So this dot and this dot moves to the middle. And this dot would move to the middle. And I would still get the exact same final result. SO4 is an ion. This -2 means there's an additional 2 electrons than what you would initially expect. So there's 6 from the sulfur, because sulfur is in group 6A. And then we're going to add 6 times 4 for the oxygens. Again, they're also part of 6A. And then I'm going to add 2 more because of this -2. When I do that, you get a total of 32. I'm going to set it up the same way, connecting all my O's to the S, filling in all my dots, and then counting up. When I count, I should get a total of 32, which is what I want. Because this is an ion, it should be in brackets with the negative charge outside. Okay, let's move on and discuss molecular shape. And then we'll come back and we'll do some more dot structures. Molecular geometry is known or is based on the VSEPR theory, VSEPR. It is an acronym. It stands for valence shell electron pair repulsion. It helps us to predict the 3D geometry of molecules as well as their different bond angles. It is based on 2 things. First, it's based on the number of bonded pairs or bonded atoms. It is also based on the non-bonded pairs. These are referred to as lone pairs because they are pairs of electrons that are all alone. We only focus on things that are bonded to the center and things that are non-bonded, so the extra pairs of electrons on the central atom as well. The theory itself states that our valence shell, which is our outer electrons, and then it says electron pair repulsion. The electrons want to be as far apart as possible. So when we draw a lot of these, some of them look very flat, when in reality, they're not flat. They are actually 3D. Let's talk about the different shapes. We are going to primarily focus on 5 shapes in this course. They are listed here. When we are discussing things that are bonded and the lone electron pairs, we're only talking about what's found on the central atom, because we don't really care about the other dots because they don't affect the shape. Something that is linear has 2 things bonded and no lone pairs, and it's going to look something like this. And a good example would be carbon dioxide. Something that is bent has 2 lone pairs and 2 things bonded. and is going to look like this. A good example is water. Trigonal planar is three things bonded, no lone pairs, and it looks exactly like what it sounds like, a triangle. A good example of this would be something like BF3. Trigonal pyramidal is three things bonded and one lone pair, and it kind of looks like a tripod in real life. NH3 is a great example of this. And finally, tetrahedral, where there are four things bonded and no lone pairs. It's going to be a tripod again, but now this tripod has a top. And CH4 is a great example here. Okay. You will want to memorize these different shapes because you will be expected to be able to go ahead and label things based on these shapes. Again, we will practice shortly. This slide here just has some additional pictures, slightly better than the ones I drew. It also includes the bond angles. You'll notice there's a lot more shapes than what you are responsible for in this course. The final thing that we have to discuss before you get a chance to try drawing some structures and identifying things is polarity. Polarity is basically defined as having two poles, or having a positive and a negative end. We often refer to polar molecules as dipoles because di means two. So, for example, a battery is a really great example because batteries have a positive and a negative end. For something to be polar as a molecule, which is different than the polarity of a bond from earlier in the chapter, it requires one of two things to be true. There should be lone pairs on the center, so certain shapes are always polar. Bent and trigonal pyramidal are always polar regardless of what other things are connected to the center. Or you could have different atoms around the center. For example, if I had CH3Br, when I draw this, the carbon's in the middle, there are three H's, and then there's one Br, and there are different atoms found around the center. Polar means different. In order to determine the shape and the polarity of a molecule, it's really important that you first draw the dot structure. So to solve this problem, you're going to first draw the Lewis dot structure. Then you're going to determine how many things are bonded and how many lone pairs you have on the center. And you'll use that to help you determine the shape of the molecule as well as its polarity. Please pause the video, draw these dot structures, identify their shape, and if they are polar or non-polar. The answers are provided for each one. As you can see, I went ahead and I drew the dot structure after I figured out the number of valence electrons each one had, verified that I was correct before identifying the shape. This first one was a little tricky because it doesn't match with the chart, but whenever you only have two elements that are combined, they have to be linear. Because these two atoms are different, it's polar. The next ones, if you drew them properly, should have been okay. As you can see, this has two things bonded, and it has two lone pairs, so it's bent. This has one lone pair, and three things bonded, so on and so forth. It is important to remember that BH3, B is an exception. It only wants a total of 6 dots. And because everything around the center is the same, it's non-polar.